Whether my screen is visible?
Yes, sir, it's visible.
So last class we did a typical prototype problem in a very generic sense, and we did one small example also just to understand how backpropagation algorithm works in reality. And the case which we have seen is particularly in the online mode of training, how it happens sequential way. Now we'll see that is there any possible to force, what is the stopping criteria? How do we uh, put forth the criteria so that the backpropagation algorithm learning should stop? How do I know this? So as mentioned this here, that we cannot show that BPA is converging, and there's no well-defined stopping criteria as such. But if you assume that W star is a minimum, the minimum weight, be it local or global. So the necessary condition we can put forth is something like this. The value of the gradient where the value of the W where the gradient is equal to 0. So if we are putting this kind of condition over there, so a simple stopping criteria we can put forth is something like this. The backpropagation algorithm is considered to have converged when the Euclidean norm of the gradient vector reaches sufficiently small threshold. So this is one way, but not the only way. Another is but here there is some problem. You see that for successful trials, learning may be long. You keep on learning if you are looking for this Euclidean norm to be considerably small value. And also it requires computation of gradient vector GW. So another way we can see that we can also use the fact that cost function or the error measure is stationary at point W equal to W star. W star you can say that you found a global minima or the value corresponding to a global minima for the synaptic weight. Now we can state this convergence condition or the criteria for convergence in a different way. And we say that the backpropagation algorithm is considered to have converged when the absolute rate of change in the average squared error per epoch is very small, sufficiently small. Now, when the question is sufficiently small, so is there any way to quantify it? How much sufficiently small? So yes, of course, here it is. So it is mentioned that like the rate of change in average error, of course, is considered to be small enough if it is lies in the range of 0.1 to 1% per epoch. Means whatever the error energy was there in the previous one, it is if it is less than or more than point or 1% per epoch, then you say that okay, it's not changing much. So my system is converged. So thereafter you stop training it. You need not to train and you can terminate the training process. Now let me summarize this BPA in this using this particular diagram. And if you see this diagram, there are two phase part for it, and one is shown in the black part, the top upper one, and there is a blue part, or what you could say, uh, whichever color you feel say. So here in this black part is indicating the forward pass. Forward pass means you have this values, and whatever the synaptic weights with which you started, you compute the output signals and you proceed till you get the output. And when you get the output, then corresponding to this pair of the inputs, you have the desired value already with you. So D1, D2, D3, let's say. And based on that and the output you found the error E1, E2, E2, E1, E2, E3, etc. Now based on this E1, E2, E3, now we have to go for back propagation. So the below this particular part of the diagram, that is this blue one, is indicating the back propagation. So here you have to compute this delta 1, delta 2, delta 3, etc. Now here you can see a marked difference between this and the diagram which you have seen previously. There is something here superscript in bracket 2, superscript bracket 1. So this superscript in bracket 2 and here 1 is indicating the level or the layer number, you can say. So this is correspond to layer 1, this correspond to layer 2. So basically it's a two-layer neural network architecture. But because it is showing in terms of signal flow graph, so that's why maybe little confusing, but it's basically two-layer architecture. So this is also one way of showing it in a complex, whenever things becomes very complex. So this layering or layering fashion, it helps. Suppose here it says that W31, so it's indicate this particular synaptic weight, the third neuron from this one getting input from the previous one, and it belongs to the second layer. So means from this one, second layer. And likewise, you can interpret yourself. Now we'll see this, our expression for the other thing are straightforward when we extending to a layered architecture, or we can say in a very more generic. Remember this particular training, I'm talking about the sequential mode only, not batch mode. So this way we can write that this one induced local field is, we know that it is nothing but the product of synaptic weight and the input it is getting from. So here, if I'm talking about the local induced field corresponding to neuron J in layer L, then it's basically is nothing but it's also the weight corresponding to that particular neuron J in layer L, and it is getting multiplied by output from a previous layer, that is L minus 1. Okay, this is normally what we do, and this is I, so whatever the value of I, and it keeps on varying depending on the dimensionality of the input you have. Then as per the, we have seen that the delta rule for the synaptic weight change as per the backpropagation rule, we have seen delta WGIN eta times delta JYI. Now here it is very clearly mentioned what it is. So if I'm talking about a change in synaptic weight corresponding to layer L, then it is nothing but eta times the local gradient of that particular neuron corresponding to the same layer L, but it is multiplied by the output from the previous layer. That's what's indicated by L minus 1, and that's we have been doing all this. And finally, this is the when I say local gradient in general, how do you compute? This is the generic formula for synaptic weight change, where local gradient plays a role, but local gradients computation has a different part. So suppose there are whatever 3-layer system is there, or Lth layer, I can say. That is, Lth layer is the output layer. So at the output layer, if the neuron belongs to the output layer, then it is nothing but the error corresponding to that particular neuron in that layer L, multiplied by this gradient of the activation function in that particular layer only, and that we could do it very easily. However, when this particular neuron is belongs to the hidden layer, then we have this kind of stuff. So we have 5' J, VJL, and remember that when I say 5J, so I'm not targeting any one particular activation function. It could be anything. It could be a thresholding function. It could be a logistic function. It could be a tan hyperbolic function. It could be a ReLU function. It could be anything. So here, that particular layer, whatever, and summation K delta K L plus 1. When I say delta K L plus 1 means I have to find, it means definitely it is a hidden layer, so definitely it is somewhere below the output layer. So I have to find, we have to find the local gradient corresponding to the layer next to the layer under consideration, which I'm talking about. Okay, so that is L plus 1, and of course this weights also corresponding to that layer, higher layer only. This is what we do. So this what, and this is a generalized change in synaptic updated synaptic weight for the n plus 1 iteration. That is this one part, and you know that this part is the momentum rule, and this is the conventional change in synaptic weight. So this is basically a generalized uh, relation for the synaptic weight updation. Okay. Now, before I go for this XOR problem, or okay, let me complete this XOR problem. So, first of all, try to understand this, what this XOR problem is. So, I'll make use of the board and we'll see this, what is this XOR problem is. So you, first of all, you must be surprised, all of this suddenly, why this guy is throwing something like XOR, which is a very simple gate, you can say that. Now, before I go about this, I want to tell you that XOR is basically a symbolic non-linear classification problem. How? So let me take you to the board. So let's say a simple cube, cube, and cube is a unit cube. Let's say which the value which we are showing here is 0, 0, x is 0, y is 0. Here x is 1, y is 0. Here x is 1, x is 1, y is also 1. Here x is 0, y is 1. Now if you take the XOR of this one, that is 1, 1, value comes out to be 0. If you take the XOR of this one, this value comes out to be 1. We know that, and this value XOR of 0, 0 is value comes out to be 0, right? And this 0 XOR of 1 value comes out to be 1. So now I can say that something like this. This point corresponds to a label 1. This corner point, so let me redraw it again. So forget about the data points. Now see that some 4 data points are there at corner, which has got label 1, this has got label 0, this has got label 1, this has got label 0. So let's say this is the data point in space, and with these are the labels, right? Now if I want to draw a decision boundary, so that here 2 types of data points are there, one is belonging to class 0, and let's say one belong to class 1, right? So I want to find a decision boundary so that I can separate this uh, 0 class from the 1 class. But here if I see that there is a problem. If I draw a decision boundary like this, so I got a 0 here, but here there is a mix of 1 and 0. Similarly, if I draw a decision boundary here, so there this part I get 0, but here again entire mix will be there. And if I draw a line like this, so this part will also have 1, 0, and this part will be a 0, 1, 0, 1. So again I am not able to separate. If I draw like this also having 1 and 0, this is also 0 and 1. So ultimately when I see this, man, what is this big problem? I'm not able to find a decision boundary which can separate this data point corresponding to class 1 and the other one corresponding to class 0. There is no straight way I can do that. So that's why this is called a no linear classification problem. That's why we say that XOR is a symbolic no linear classification problem. Now, what do you mean by this symbolic? I'll just explain now. Now, suppose you have designed a neural network and you claim that any data which is no linear separated can be classified using your proposed network architecture. Now, there are theoretically infinite number of scenarios which are non-linear. So I cannot keep on testing each and every one of them. So I can have some test suite data which is known to be non-linear, means already I know that they are non-linear. Now, if your algorithm or then your network architecture does a good job on the known and known data set which is non-linear, I can say that any non-linear things can be classified using your proposed algorithm. So that's why we say that XOR is a symbolic no-linear classification problem. Now the question is, how does it do? So basically, for this we have to go a little bit here and try to understand the decision boundaries and all the stuff, means how it really happening. So I can say that this is let me say a simple neural architecture. Basically, a single neuron we have to consider. Single neuron. Just a minute. Let me explain this. So let's say a simple architecture I'm taking, a simple, very simple neuron, one single neuron system, and it is taking input x1 from here, let's say x2, and let's say it has some bias also. Let's say it is some bias, having bias, and let's assume that this value is 2 and 2. This is assumption I'm making, nothing more than that. And also I can have any other inputs also we can think of. Now let's say my x1, x2, x1, x2. That is x1 is 1.5 and x2 is 0. Let's say simple. Now forget about this one. At this particular point, I just want to write y. So y will be nothing but w1 x1 plus w2 x2 plus b, right? So this is what we have. And we know that whenever the equation is linear, for to find a decision boundary, we equate this to equate to 0. Now when I write this equation, so I'll write like this, basically 2 into 1.5 plus of course 2 into 0 plus b. B is if b is not known to me, so I can just find it out what is happening, equating to 0. So it's basically uh, b comes out to be -3, so I can write here -3. Now if I just have a thresholding function, let's say thresholding function, and that is a basically straight away Mac-Lispitz model neuron, where the value of thresholding function is either 0 and 1. Whenever the value is greater than 0, it is mapped to 1. Whenever it is less than 0, it is mapped to 0. So if I go for this, of course here it is not directly here. You are also not observing. Actually, phi is working. And for computing the decision boundary, we write like this. From there, I got this one. Now, when we go for y, so which you have seen phi here, and whatever this value, when including everything, you substitute all this stuff. And so for the different values, if I'm writing here x1, x2, and let's say y, so you say here 0, 0, 0, 1, 1, 0, say 1, 1. And if you are thinking about is an AND gate, now you'll be surprised why all of suddenly this guy is showing the AND gate. Hold on for a minute, I'll explain. I want to say something. So this is, you know, the behavior of this AND gate. So now these weights are known to you, let's say. And when I'm showing it, actually what I'm trying to show that XOR problem can be solved using the combination of OR and AND gate. So first of all, I have to write a neural network system which mimics or emulates the behavior of an AND gate. So which have with these values, it really shows the behavior to me AND gate and how. So I'll show you. So here W1 x1 plus W2 x2 plus B, which of course here you have 2 x1. X1 means if I'm taking this first case, if I'm saying 0 plus 2 dot 0 and minus 3, which comes up to phi minus 3. And we know that whenever thresholding function is there as a negative, so this value comes up to 0, right? And again, when if I take any other case, if I take the second case, and this is the first case, first, second, third, fourth. So I have this 2 dot 0 plus 2 dot 1 minus 3, so value comes out to be how much? Minus 1, again 0. Now if I consider third case, this also again comes out to be saying it will also comes out to be minus 1 only, so 0. And fourth case, if I say, so it will be phi 2 1 plus 2 1 minus 3, so phi 1, the positive value, so 1. So if you see that for this combination of this combination of weight and the synaptic weight and the bias, the two input system is there, so it is this particular neuron is behaving, or you can say that emulating the behavior of the AND gate. Yes or no? Hello? Yes or no?
Yes, sir.
Yeah. So basically what it's doing is something like this, that it is, if I'm trying to plot it into two-dimensional, something like this. So basically this particular line, it is finding one. This is x1 and x2, this kind of. Now, similarly, if I, and now you may ask a question, man, do I have to remember these weights? No, you can try yourself. Probably you may come out with another set of synaptic weights and bias for which your neuron may be behaving like an AND gate, but you have to check yourself. So it is not a straightforward global rule that only this combination of synaptic weight and bias the network is going to emulate like a AND gate. There could be any other value, but you have to check it. So it is something like hidden trial you can think of doing initially. Now let me take another situation, and I'll slightly change this one and see whether how our things are behaving. So if I take this again, let's say to input system, and this time I'm just call w equal to 1 and w2 equal to 1. Let's say x1, x2. Let's say this is my bias, which I don't know currently, let's say, and this is my y. So you know that when you find this local induced field, so local induced field where the decision boundary is compared to 0, so basically it is w1 x1 plus w2 x2 plus b, and assume that, let's assume that your x1 or basically x vector is 0.5 and 0, basically x1 is 0.5 and x2 is 0. So this value of when you equate to 0, so it will be how much? It will be 0.5 into 1 plus 1 into 0 plus b equal to 0, which comes out to b equal to minus 0.5 or minus 1 by 2 straight away. So I can write here this is minus 1 by 2. Now let's say this combination we have. So we found a configuration for our neuron system. Now I'll go for the same combination of x1 and x2, and let's see what happens. Again, we have the neuron which you consider is a Macaulay-Spitz model neuron only, which use activation function as threshold, thresholding function as activation function. So I can write here the first case whenever 0, 0 is there. So I can write phi y equal to phi 1 into 0 plus 1 into 0 minus 1 by 2. So phi minus 1 by 2, so comes out to be 0. Second case, I can take it where the value is 0, 1. So 1 into 0 plus 1 into 1 minus 1 by 2. So value comes out to be 1 by 2. Value is greater than 0, so this value comes out to be 1. Third one is phi. I can have 1 plus, let's say, uh, 1, here it was. So again for this also, and fourth one, of course, 1 into 1 plus 1 into 1 minus 1 by 2. So it comes out to be 2 minus, so basically 3 by 2, so 1. So if you see this slight tweak in the architecture values, synaptic weight values and bias value will make or will enable the neuron to behave like a OR gate. If you see this expression, these are nothing but the OR gate only, behavior of OR gate. Now with this, we'll see that how it is really working to helping us to find the solution for that. So what solution we are looking for is something like this, that this was a corner for this. Here we saw 0, here we saw 1, 0, 1. So somewhere, so this part you are getting due to the AND portion, right? AND portion means here everything is 0 and only 1 was appearing. Another portion was getting due to the OR. So in between this boundary, so if you fold it like you think it in that way, so what is lying beyond this boundary is also 0. Whatever lying below this is also 0. What is in between basically belong to the label 1. So let me take you the slides back and see that's how it is happening. So as I mentioned, it's a symbolic. So here it is. So if I'm taking, so one of them, this particular part is behaving like your AND gate. Another one, when those are the inputs you have taken. So when you say that those are the inputs you have taken means what? So you saw that whenever this 0, 1 was there, again 0, and this part was 0, 0, 0, 0, 0, and this was something of that form. And so this is A and B, you can say this particular part. This is neuron, another neuron which was working like this. This is like OR gate, which you've seen. Of course, the values of the synaptic weight and biases will be different, and we combine them and give it to one more neuron, then it will behave completely different way. So I'll show you. So it is something like this kind of architecture you can form. So you can have this way, and we'll try to trace this particular path, how it's going to be. You have neuron 1, so this particular part is one particular. So these values are quite different, which I have shown as an example. Remember that. So this is whatever I have shown is just one case for emulating a, or you can say designing a neuron to behave like an AND gate, or designing a neuron to behave like OR gate. There could be theoretically infinite possibilities are there, so that they will emulate. So here when we connect the 3 neuron system, then it behaves like a XOR gate. So how I'll show you. So once you have this, so you can combine it up. So what we have to do is this. Whatever the value of 0, 0, etc., this is known to you, 0, 0. So we have to compute the value y here. This particular y, let me call it y1, this value y2, and those y1 and y2 combination acts further and multiplied here, this one, and this particular bias passed through this thresholding function. And of course, everywhere thresholding function which you are taking is basically Mac-Lisput's model thresholding function, and the value which comes out to be, you will be surprised to see that it solves the XOR problem. So ultimately, what is the objective of this particular analysis or this POC or proof of concept is that a MLP, that is multi-layer perceptron, these are neurons only, but multi-layer system can solve an XOR problem, which we saw that it is not possible to solve using a linear boundary, but it is able to solve the perceptron, this one, linear non-linear problem. So this is the POC kind of thing, right? So with this, we'll proceed further. So here we can see that this is a decision boundary. Basically, the first one is decision boundary by neuron 1, and this is decision boundary formed by neuron 2, and this is a combined one decision boundary formed by complete network. So this is output for one thing. Now, before I go for this heuristics I'm talking about, means how to speed up the process and all. So we'll take a quick, what should I say here? And we'll go for the quiz now itself. And this quiz will be for 4 minutes. I'll time. So your time starts once I display this. Make sure that you get it. Actually, it's for 2 minute job only, but let's say that you have. So in my watch, it says for 2:33, 37. I'll stop. Last 1 more minute.
Excuse me, sir.
Yeah.
Sir, I'm not really able to open the quiz.
What I can do in that?
So could you please give me 2 more minutes?
Okay, we close now. We'll close now. Okay. We are back. Now, let's get back to the class now. So whatever we have done this so far, this MLP, almost 2-3 classes we have been doing is quite elaborate chapter. And why I emphasized and invested so much time in this is basically this is the basic building block of any course on neural network. There are many other types of learning which are variants of BPA only, slight tweak here and there to optimize the performance of BPA. So that's why we have invested so much time to understand the BP backpropagation algorithm from the scratch. We derived it also. We have taken one example, even a complex example, and we give a generic solution using paper pencil method, how it basically we have traced it. And we have seen also one simple example and shown yourself that yes, it's learning. And then we have talked about certain about the criteria for stopping, learning rate, and how do I speed up the process. So we saw last class momentum concept, etc. Apart from that, there is some sort of heuristics. When I say heuristics, so basically heuristic is there's no strong and fixed rule for doing something. It is most of the time it's like based on some empirical observations. You found some way to speed up the process. How do I go for that BPA can be more efficient or the learning can be speed up? So we'll see now. So and with that, today I'll possibly close that, and this new things will start in the next class. So we have seen so far for the next topic which we are talking about is heuristic for making BPA perform better. Now perform better. So how? So as I told you that basically there are these are the heuristics, or you can say that people have found empirically that this works to speed up the process. So two aspects you have seen. One is sequential, another is batch mode. So sequential, you know that always also called as online, and the batch mode. So sequential mode of backpropagation algorithm is computationally faster than the batch mode, especially when the training data is large and redundant. Okay. So you have also seen that one particular problem was given today, that a design this matrix is given to you, basically nothing but a data set. And for that, the correct answer is that basically online mode of learning is more suitable. For a simple way that if you see the design matrix, there are redundant rows. The repetition of rows are there. Whatever the first row and third row is same. So means when I'm doing this, so what happens? We are training example by example. So something one particular example has been already presented to the network. It need not be presented once again. So this is the advantage you get it off the shelf using a sequential or online learning mode of the system. Whereas if you have used this batch mode, then you blindly keep on applying each one of them till your entire one epoch is completed. Now this when you say that so one means that we choose the which one is more suitable, sequential or batch. So we see the situation, the data, how if it is large and redundant information is there, we don't go for batch, rather the sequential or online mode is more appropriate. Now then we see that another aspect is that if I can maximize the information content, then also speed up the learning. So when it comes to that information content, maximizing the information content, so first of all, what do you mean by information content? How do you measure the information content? Hello? Any rough idea? How do you measure the information content? Anybody? Say yes or no. Hello. Does anyone of you know about the information content? How do you measure or quantify that yes, it is more informative, it is less informative? When you see this, huh?
Like that, Guinea index and other stuff like that.
Gaming index. Nothing of that sort. So just let me take you back to the information theory. Little, not much. So probably I think you had some course in communication theory, right? So you might have heard about this entropy, before that this information content and all. So before, forget about all this entropy, information content or information theory. Say that you know that in Manipal weather in April or March is fully bright weather. Sun is at its peak and it's like shining like anything. So and then I come for the class and I say that today it is going to rain heavily in Manipal. If I give this statement, outside you saw, man, it is completely bright, and how this guy is saying this. So effectively, the probability for rain is zero. Probability for rain is zero, but I'm giving this statement to you. So basically, when I giving this particular statement to you, so this thing is one idea coined by this Shannon, Claude Shannon, way back in 1948. He said that how do I measure this information? When I measure this information, he said that take log 1 by p. When I take log 1 by p, so what happens? This becomes infinite, so value is very high. Information content is very high. When I say whatever information I'm giving to you, from your obvious observation, it is zero. It is not going to rain, but I say it is going to. So it means this is going to be information is high. So what I'm trying to say, if something is more probable than information content is less, because you know that's obviously going to happen. What's the big deal, right? But something is less probable, the probability is less, the information content for that is more. So this is what I'm trying to say. Now, then why I'm just winning this story here now? It is something like this. So we have to, after training one particular example, then you have to choose one example such a that it is drastically different from the previous one. Let's say at time instance n, you are giving some example, say nth example, whatever you have seen. Now you are choosing another example whose values are just near to it. Means earlier, let's say it was 1, 2, 3, 4, 5 different attributes. Another one is having 1.2, 2.3, slight change. So do you think that the synaptic weight updation will go drastically toward the global minima? No, slight change will happen. However, if I choose a example whose values are quite different from the what has been given now, So that will maximize the information. It's not very obvious that this is going to be there. So how it is done, that is shown here. So every training example presented to BPA, that is backpropagation algorithm, should be chosen such that information content is largest possible for the task at hand, whatever the task may be. So how do you do this? So for example, we use an example that results in the largest training error. So that kind of example you choose. So then it will give a largest training error. So definitely if training error is large, you know that backpropagation will happen and maximum change in synaptic weight will happen. So it will speed up the process. Another way is that use of an example that is radically different from all those previously used. That's what I was saying that. So don't use in a very systematic way, in a serial way, that you go one by one without bothering that which is having something. So let's say you are having you are training a system with all cat, dog, and something another animal is there. So cat and dog are so many, and you are training this, and all of sudden, so instead of giving the next example with cat and dog only with a slight variation, give some other animal which is there in your data set, which is completely different from this. So it will give a speed up the process for learning because error will be more. Error will be more, so back propagation, as you know, that it propagates back the error, and synaptic change will happen. So this will be more. So this is one of the way. Also, activation function when you're choosing, so what kind of activation function you should choose for? So they say that basically to speed up the process. So this is basically now becomes a classical. There are another activation function which can do this the same thing. So you see that MLP, that is multi-level perceptron, when trained with BPA, learns faster when anti-symmetric form of sigmoid function is used instead of non-symmetric. So popular example is basically anti-sigmoid sigmoid function is basically hyperbolic tangent function. Okay, so hyperbolic tangent function, you have something like this. And why is it so? And also it has been found empirically and experimentally for these values of A and B's. So when you say phi v equal to 8 and hyperbolic VV, so this value of A 1.759 and plus and minus, and for B equal to 2.3. You are getting an anti-symmetric sigmoid function. The recommended target values are plus and minus 1, means say the maximum value will be plus and minus 1. For this kind of thing, this will also speed up the process. Why is it so? Basically, what happens that when you are not having something like this, it puts those things in saturation. So it's avoid from going up to saturation. Another is that the target values. Target values means desired values, means how do I find it and what value it should be. So they say that it must be chosen within the range of the sigmoid activation function. A range of sigmoid activation function, this value should be changed, should be chosen. And the desired response dj in the output layer should be offset by some amount epsilon away from the limiting values of the sigmoid function. Means the what is the limiting value of sigmoid function? So plus minus epsilon should be used as far as dj value is concerned. Means if the limiting value is a, let's say, so your dj value should be like limiting value means either plus 1 or minus 1, likewise, or whatever plus 2 or minus 2, you can say that. So desired value should be a minus epsilon or a plus epsilon. This one it should be. And here epsilon in the particular case was 0.7159. Also, there is a thing that normalization of the inputs. So instead of directly giving the input to the system, means the training itself directly, can we do something with the training data itself, what you call as a pre-processing, right? So each input variable should be pre-processed to that its mean value is close to 0. Now tell me that if you have a data set with you, training data, and if mean is not 0, what will you do so that it mean becomes 0? What transformation you can apply? Any idea?
Zero mean transformation, where we normalize the
How do you do that?
we subtracted from the mean and divided by the Variance.
So for dividing variance of the each attribute leads to unifying the variance, but subtracting each and every this one will take you to the zero mean. Of course, we'll see more on this. So, and also to accelerate BP, input nomination must include the following. And also, we also make this standard deviation that could be unity is possible. So we do this particular process. Input variable contained in the training set should be uncorrelated. We somehow a correlation we have to get away with. So this we can do using PCA, and PCA means a principal component analysis. And decorrelated input variables should be scaled so that their covariance are approximately equal, thereby ensuring that different synaptic weights learn at approximately the same speed. So it should not happen that one is learning fast, one is learning slow. So it should not be the case. So they say that by applying this, you can further speed up your backpropagation learning in using backpropagation algorithm. So they have tried to show this. Suppose this is the original set of data points, and when you apply the mean removal, so it becomes like this, something like this. Let's say it moves towards the origin. And when you apply decorrelation, so it is basically it is something like this. And when you apply covariance equalization, so this transformation, they are not exact, but some just giving some sort of a gist that when you apply from from this to this particular process, now now if you apply your backpropagation algorithm, so learning will be faster. Now there is a very good thing. Initially, if you remember that we said that when we apply backpropagation algorithm, we'll try to apply, we have to start with some initialization, right? Some initialization. So initially, either we can initialize random weights, or is there any way that we can initialize in such a way that it can further speed up the process? So there is a way that you can make an informed initialization. Informed initialization means there is some way or technique you found that if you apply, and with that particular initialization of the synaptic weight, and then you train, it will be much faster as compared to the arbitrary initialization. So how that will happen, and that we'll see through a particular analysis now. So basically a good choice of initial values of synaptic weights can be of tremendous help. Let's see this. So when you say good choice, so what do you mean by good choice? So let's see here a good choice and how it can be. Majorly we'll try to understand what do you mean by good choice. So let a MLP without any bias, and we are applying a hyperbolic tangent function for its activation function, let's say. So no bias and applying tan hyperbolic. Now when we say this Vj equal to I equal to M, let's say it's basically M dimensional input it is giving. So Vj Rwji, Yi, this we know that is basically local induced field. And also we are assuming that input applied to the neuron has zero mean and unit variance. So whatever the training data you have, let's say previous to this, you have already done this pre-processing you have done, and you ensure that the mean is 0 for all I, and the variance is equal to 1. Okay, variance is equal to 1 for all I, means for all the example. Now also we are assume that inputs are uncorrelated. When I say inputs are uncorrelated, it means that when I say that expectation mean of this expectation operator apply over the two true training example y1 and yk or yij, whatever you can say, that whenever the value remains, whenever their same example are there, so this value comes out to be 1. Cool. Otherwise they are 0. You can say they are uncorrelated. So you have also ensured that this uncorrelation has happened. Now synaptic weights are drawn from a uniformly distributed set of numbers with zero mean. So imagine that you have taken this, initially you are going to take this synaptic weights. So you're chosen in such a way that they are uniformly distributed and the mean is 0. So this is how Wj, all these values comes out to be 0. and variance is something like this. So we are not saying variance is 0 as well or 1. No, this is something variance is there, but it is uniformly distributed and 0 mean. So with this kind of assumption, let's see, can we come out with some a requirement to define the good choice for initialization of the synaptic weight? Let's see how. So this with the assumption we are only making. Let's finally we have to put for the condition on W only. Now, so here we'll go one by one. So expressing the mean and variance of the local induced field, we saw mu v, so EVG, so E and this we say for V. So I equal to 1 to M, WGI by I equal to, you know that basically expectational averages or the time averages basically linear operators. So we can take it inside. So when E goes inside, E can be applied on this, E can be applied on this, and this value comes out to be 0. This value comes out to be 0 because you saw that the mean of the data is also 0, mean of this is also 0. If either one was 0, that is also 0. And when I find this for local induced field, so you found that okay, the mean is 0 for the local induced field. Now we'll say this variance for this. So variance is Vj minus mu v and square it is. So when I go for this one, mu v, you found that it is 0, so this is nothing but Vj square. When I write this something Vj square and V is something like this and square function is there, so I can put two summation here, I equal to 1 to M or K equal to 1 to M, or I could have mentioned something else. So WGI and WJK YI YK, actually it should be written WGI YI WJK YK, and it is written in all this combined form, so this all weights together, all y's together. Now when we apply E, so we'll apply E over the only synaptic weights and over the this input part. So E of WGI, WJK, E of Y and YI and K. So once you have this, so basically if you want to tweak it across, you saw that they are basically whenever we saw that they are uncorrelated, means whenever I is equal to K, the values was 1, otherwise it is 0. So we are assuming that, let's say this I equal to K. When I say I equal to K, it becomes W square JI, and this anyway it becomes 1. And once this comes, this value you already seen in the previous slide, this we are saying that sigma square W, only this much, sigma square W for this much. And here you saw that you are summing across this, and when you sum across this, there are m number of this one, right? So we found some sort of relation between the synaptic weight variance and the variance of the local induced field, and we'll see that what is that. So a good strategy for initializing the synaptic weights so that the standard deviation of the local field of a neuron lies in the transition area between the linear and saturated parts of the sigmoid activation function in that. So for a hyperbolic sigmoid, this objective is satisfied by setting this sigma equal v equal to 1. When you have this something like this, then you can say that m equal to you got this kind of value, so 1 by sigma square, sigma w square. So you have something like this. So once you have this, now we're trying to say that for the uniform distribution from which the synaptic weights are selected to have 0 mean and variance of equal to the reciprocal of the number of synaptic connections of a neuron. Or you can say that whatever the dimensionality of your input is there, so if you are able to choose your synaptic weight, initial synaptic weight from a distribution which has got 0 mean and variance, standard and variance equal to the reciprocal of this dimensionality. It is 1 by m root m, something of that. So if you are able to do that, then with this initial synaptic weight, if you have it, it is more informed and the learning is faster. This is what it means to say. Now, learning from this hints, this is also possible. if there is some sort of hint is given, okay. If you've seen that if some problem is given to you and problem looks very complex, so sometime in exam this teachers give some hint, use this hint, and using that hint probably it will give you some idea and you may be able to speed up your solving. In the same way, some sort of hint. So process of learning may be generalized to include learning from hints, which is achieved by allowing prior information that we may have about the function f to be included in the learning process. Okay, so if you have some sort of prior information, so you can include that also. And learning rate, we have seen that. So how can I use the information of learning rate to speed up the process? So eta should be smaller value in the last layers than in the front layers. The reason for this is very obvious. When you go for the last layer, you are taking a baby step to ensure that you are not going to overshoot the global minima. Initial layers, if it is the eta is large, not a problem because you want to speed up the process. But till for the last layer, when you come, the value should be small. So instead of taking a uniform value of eta, that is the learning rate, either 0.1, 0.2, whatever it may be, it is advisable that the value of eta chosen for the last layer should be small as compared to the initial layers or in between layers. You can see that. So while neurons with many inputs should have a smaller value of eta than neurons with few inputs, so as to maintain a similar learning time for all the neurons in the network. So with this, we'll conclude this particular chapter today here. Now, if you have any doubt whatsoever, let me know. Please shoot it now. I'll try to answer now itself. Hello? Does anyone of you have any query? Okay. So if you don't have, so we'll disperse today now at this only. And before resuming a new chapter, so I want to start afresh from next class. And I want to tell you that this tomorrow you have a contact hour, so I'll be available in room number 315 from 2 to 3. So if you are here in Manipal or not in Manipal still, so I'll be available through online also, but I would be happy to see some of you. If you have any query, I'll be available in room number 315. Okay. Just be there, be there.